Question 1. In the Geiger-Marsden experiment, alpha particles were directed at a thin gold foil. Which of the following shows how the majority of the alpha particles behaved after reaching the foil? Okay, there were 3 observations in the Rutherford's experiment. The first observation was around about 99% of the alpha particles went straight through. And I would suggest that 99% are classed as the majority. The second observation was that some of the alpha particles were slightly deflected. And the third observation was that 1 in 8,000, not exactly, around 1 in 8,000 of the alpha particles were completely rebound. So, given this question is talking about the majority, we're looking for an answer that shows most of them going straight through with 1 or 2 or some being deflected. So our answer here is A. Let's go to the others just to make sure that we can accurately discount them. In B, we have all of the alpha particles showing some form of deflection, which is not true. In C, we have all of the particles showing rebound, not true. And in D, we have all of the particles being completely stopped by the foil, so that's not true either. Question 2. The diagram shows 3 electron energy levels of an atom. Which transition results in the emission of a photon of the longest wavelength? Before we actually answer the question, let's look at the emission of a photon. When an electron loses energy, that energy is given out as a photon, so it's an emitted photon. So for this question, I'm thinking, in what direction does the electron lose energy? If it loses energy, it becomes more tightly bound to the nucleus. And if it's more tightly bound to the nucleus, it goes down an energy level. Now remember, the energy levels go in this direction. N equals 1, N equals 2, N equals 3. So for an emission of a photon, we're looking at moving down, the arrow down the way. So that rules out A and B. Now we want one with the longest wavelength. And the longest wavelength means wavelength is big. That means that frequency is small. And given that energy equals HF when we're talking about a photon, if we have a small frequency, we have a small energy. And a small energy means a small change in energy between the transition lines. So we want the smallest gap between the energy levels that's going down the way. The answer is D. Question 3. Explain how atomic spectra provide evidence for the quantisation of energy in atoms. This is an explain question, so I'm going to use my explain quadrant. And in the first quadrant, we look at a diagram. The diagram I'm going to look at is energy levels in an atom. And if they gain energy, they're moving further away from the nucleus to become free. And if they gain energy, that's an absorption photon or absorption spectra. And if they lose energy, that means going towards the nucleus, and that means they emit a photon. And I'm also going to draw a spectrum here. Okay? And these are just random lines, but these sorts of things are going to inspire me as I write my explanation. The next thing I'm going to do is write down keywords that I want to include in my explanation. I want to use the word spectra. I want to use the word discrete, because that's another way of describing quantization. I want to use the word frequency or wavelengths, maybe both. Definitely want to use the word photon. And I definitely want to use the words energy levels. Okay. Are there any phrases I want to include or well-known relationships? I want to use the term spectra have discrete frequencies or wavelengths. I want to say higher energy transitions relate to higher frequency photons. But most of all, I really want to try and link atomic spectra for evidence of quantization of energy in atoms. Okay, I'm going to do that in 3 marks. Mark 1, and we'll say atomic spectra have discrete spectral lines with certain frequencies. Now we want to start linking the frequencies of these spectral lines to energy, because we're looking at quantization of energy in atoms. Each photon in these spectra have energies of E equals hf. And now we want to finally relate it to the quantization of energy in atoms. Okay, so these discrete energies of photons arise from discrete energy levels in atoms. Each transition between energy levels corresponds to the frequency of photon in spectra. I'm going to take a moment just to check that I've included everything. So go to our keywords. Have I used the word spectra? Yes. Have I used the word discrete? Yes. Have I used the word frequency and wavelength? Yep. Have I used the word photon? Yep. And have I used the word energy level? Yes, I have. Have I used my phrases? Spectra have discrete frequencies and wavelengths? Yep. Have I said higher energy transitions relate to higher frequency photons? No, I haven't. And do you know why? Because it doesn't ask you about the relationship between the frequency of the photons and the spectra. It says, explain how atomic spectra provide evidence for the quantization of energy in atoms. This actually wasn't related to the question, so I'm glad I didn't write that down. I'm really pleased with that answer. Hope you are too. Question 4. Which statement about atomic spectra is not true? Okay. A. Atomic spectra provide evidence for discrete energy levels in atoms. Well, that is true. B. Emission and absorption lines of equal frequency correspond to transitions between the same two energy levels. Well, given that E equals hf, so the change in energy between energy levels equals hf, then if it's the same frequency for absorption and emission lines, it must be the same change in energy between those transition lines, which means it must be the same transition. So that's correct as well. C. Absorption lines arise when electrons gain energy. I just want to take you to the diagram of the energy levels here. Bear with me a second. Got n equals 1, n equals 2, n equals 3, n equals 4, and then we've got up here n equals infinity. And this, at this point here, the electron is free. So to get the electron to be free, we have to give it energy to escape the ground state and escape the electrostatic pull of the nucleus. So an absorption line is when you give the electron energy to escape. Is that true? Absorption lines arise when electrons gain energy. Yes. So this one must be wrong. D. Emission lines always correspond to the visible part of the electromagnetic spectrum. That is not true. If you look at a spectra through a UV lamp, this is UV, this is visible, this is infrared, you will still see lines at all of the parts of the spectrum. It's just that you need a detector to see it in the UV side and a different detector to see it in the infrared side. The detector we use to see the visible light, of course, is our eyes. But if you have an infrared detector here and a UV detector on the UV side, you would see those spectral lines too. So our answer here is D. Question 5. The energy level diagram for an atom has 4 energy states as shown. What is the number of different wavelengths in the emission spectrum of this atom? Okay, for emission spectrum, we have the electron losing energy, so it's getting closer to ground state. So we've got a downwards arrow. And we want to know how many number of different wavelengths are there. So how many different transitions are there down the way? Well, we can do this one. We can do this one. We can do this one. We can then go from here down to there. We can go from here down to there. And finally, we can go from here down to there. That's the number of possible transitions we can make going down the way, and that equals up to 1, 2, 3, 4, 5, 6. 6 different transitions, which means 6 different wavelengths. Question 6. Rutherford constructed a model of the atom based on the results of the alpha particle scattering experiment. Describe this model. You have to be careful here. This question does not say describe the experiment. This question says describe the model of the atom. Atoms are mostly made up of empty space. 2. The nucleus of the atom is positive. And 3. Most of the atom is concentrated into a very small nucleus. Have we accurately described the model of the atom? We're nearly there. We haven't mentioned electrons. So what we would say is electrons orbit the nucleus. And I think we're there. Question 7. The diagram shows the position of the principal lines in the visible spectrum of atomic hydrogen and some of the corresponding energy levels of the hydrogen atom. I just want to look at this diagram first. The one that I showed you in step 1 had the energy shown in MeV, mega electron volts, and this one has the energy shown in joules. So we're noticing slightly different numbers here. It would have been 13.6 MeV if it's in mega electron volts, but of course this is given in joules, and that's why that looks unfamiliar. A. Determine the energy of a photon of blue light emitted in the hydrogen spectrum. What do we know? Well, we know that blue light has wavelength of 435 nanometers. We want to find out what energy is, and we know the equation E equals HF. We don't have F. Wait a minute. It is light. We know that light travels at the speed of light, which is 3 times 10 to the 8 meters per second. And we know that C equals F lambda. So F equals C over lambda. Let's take this equation here. E equals HC over lambda. Let's pop all those numbers in. H is a Planck's constant. You'll find that on your data booklet. And that gives us an answer of 4.57 times 10 to the minus 19 joules. It looks like we can give our answer to 3 significant figures, given that the data is in 3 significant figures. So I'm happy to leave it at that. B. Identify with an arrow labelled B on the diagram the transition in the hydrogen spectrum that gives rise to the photon with the energy in A. Yikes, that's a bit of a mouthful. Let's go back to A. We know that the change in energy required to cause this photon of light is 4.57 times 10 to the minus 19 joules. So we have to go to this energy level diagram and find out which transition is equal to 4.57 times 10 to the minus 19 joules. And before we do that calculation, we must remember that the photon is emitted. That means that the electron is losing energy. So we're looking at an arrow going down the way to show that it's an emitted photon. If we make that energy level from here to here, then the energy difference is only 3.02 times 10 to the minus 19 joules. It's not that one. So we need to look for something that's significantly bigger. Let's choose this one. 5.44 minus 1.36 gives us 4.08 times 10 to the minus 19. That's not 4.57, it's not that one. I think we all know it's going to be this one now, don't we? We've got 5.44 minus 0.870 gives us 4.57 times 10 to the minus 19 joules. That is the correct one, and we're going to label that B. And finally, question 7C says explain your answer to B, and that's 2 marks. So the first explanation will be the difference in energy levels is 5.44 minus 0.870 equals 4.57 times 10 to the minus 19 joules. This is equal to the energy of the emitted photon. I don't think we're really there yet because we haven't said why it's an emitted photon. So we have to say energy is lost by an electron when a photon is emitted. And I think I'm going to finish that off by saying this means the electron will move from a higher to a lower level. And I feel I'm pretty happy with that answer. Question 8. Which of the following atomic energy level transitions corresponds to photons of the shortest wavelength? If we have a short wavelength, that means we have a high frequency, which means we have a high energy. That means our change in energy has to be big. Which is the biggest change in energy? I would say that's C. Question 9. The energy levels for an atom are shown to scale. And you can see we've got n equals 1 here, n equals 2, n equals 3, n equals 4, and you can see that those energy levels are getting closer to each other as the energy increases. A photon of wavelength lambda is emitted because of a transition from E3 to E2. Which transition leads to the emission of a photon of a longer wavelength? Right, if we want a longer wavelength, we have to have a smaller frequency. And if we want to have a smaller frequency, we have to have a smaller energy gap. So E3 to E2 looks like this. And we want to have a smaller energy gap than that. So we have to go from E4 to E3. Our answer is B. Question 10. A proton, an electron and an alpha particle are at rest. Which particle has the smallest magnitude of ratio of charge to mass, and which particle has the largest magnitude of ratio of charge to mass? Okay, let's look at a proton first, and we'll list their charge and mass. The relative charge of a proton is +1, and the relative mass of a proton is 1. Electron. The relative charge is -1, and the mass of an electron relative to this proton of 1 is, and let me just show you how I do this calculation. This is the mass of an electron. This is the mass of a proton, and that gives us a value of 0.0005. So the mass of an electron relative to the mass of a proton, if we call the mass of a proton 1, is that. And an alpha particle. Its charge is +2, and its mass is 4 because it's got 2 protons and 2 neutrons. Now we want to know what the ratio of charge to mass is. So charge divided by mass for the proton is 1. Charge divided by mass for the electron is 1,836. And charge divided by mass for the alpha particle is 2/4, which is a 0.5. So which has the smallest charge to mass ratio? That's the alpha particle. And which has the largest charge to mass ratio? That's the electron. The answer is A. Question 11. 4 of the energy states for an atom are shown. Transition between any 2 states is possible. What is the shortest wavelength of radiation that can be emitted from these 4 states? So if we're looking for an emitted photon, we're looking for the electron to lose energy, so it moves down the states. That means that our arrow is going to be moving downwards. That's the emission part of it sorted. What's the shortest wavelength? Well, if it's a short wavelength, that means it's a high frequency, which means change in energy is the highest. So what's the biggest change in energy we can see between these states? Well, the biggest change in energy downwards is E4 down to E1. That's the biggest change in energy. And what we're looking for in this answer is an expression for the wavelength. So we can start with this. Delta E equals HF. We're obviously dealing with wavelength rather than frequency. So let's adapt our energy formula for the wavelength. And we want to rearrange for wavelength. So lambda equals HC over delta E. We know that the change in energy is from E4 to E1. So HC over E4 minus E1. Our answer is A. Question 12. A simple model of an atom has 3 energy levels. The differences between adjacent energy levels are shown. What are the 2 smallest frequencies in the emission spectrum of this atom? So again, we're looking at emission spectrum, so we're moving down the energy levels, and we want to know the 2 smallest frequencies. There are 3 possible frequencies here. If we name the states n equals 3, n equals 2, and n equals 1, the 2 smallest energy changes are from n3 down to 2 and from n2 down to 1. That's going to give us the 2 smallest frequencies, but we actually need to know what the actual frequencies are. And what we're given is the energies. So for n3 to 2, we know that E equals hf. So F equals delta E over H. Let's carry on with that F. So delta E is 6.63 times 10 to the minus 19 divided by H, which is Planck's constant, which is 10 to the minus 34. So that gives us a magnitude of 1 times 10 to the 15. So one of our answers is going to include 1 times 10 to the 15. We can rule out B. The other transition was from N2 to N1. And we're going to do exactly the same. Delta E over H. Delta E in this case is 13.3 times 10 to the minus 19, which you'll of course know is 2 times 6.63. And divide it by Planck's constant. And what we're looking at here is 2 times 10 to the 15 hertz. Our answer is C. Question 13. The diagram below shows 4 energy levels for the atoms of a gas. The diagram is drawn to scale. The wavelengths of the photons emitted by the transitions between the levels are shown. What are the wavelengths of spectral lines emitted by the gas in order of decreasing frequency? The question obviously shows us the wavelength of the emitted photon, but we're asked to order them in terms of decreasing frequency. So let's go with the highest frequency. Given that delta E equals hf, the highest frequency would be the transition that has the highest delta E, and that's lambda 4. So lambda 4 is going to be our first one because that's the highest frequency. Then the next highest frequency will be lambda 1 because it's got the second largest energy transition. So lambda 1, then it'll be lambda 2 and lambda 3. Which answer gives us that there? That is answer B. I've got a feeling we're getting quite good at these transition energy level questions now. Let's keep going. Question 14. Some transitions between energy states of a particular atom are shown. Energy transition E3 gives rise to a photon of green light. So this is green light. Which transition will give rise to a photon of a longer wavelength? Delta E equals hf, C equals f lambda, so f equals c over lambda. Delta E equals hc over lambda. Lambda equals hc over delta E. If we want the largest wavelength, we want the smallest change in energy. That's E4. Our answer is C. Question 15. The energy levels of an atom are shown. How many photons of energy greater than 1.9 electron volts can be emitted by this atom? Big diagram here. Let's look at all the possible transitions. So there's 6 possible transitions. Which ones of them have energy differences greater than 1.9? Let's go here, this one here. Well, we know that that one is less than 1.9 because it's 0.5 minus 0.9, which is 0.6. Here we are. What about the next one? 3.4 minus 0.9 gives us an answer of 2.5. So this one is correct. This one's obviously going to be bigger than that. Now we're looking at the fourth one along. 3.4 minus 1.5 is 1.9, but the question asks for photons greater than 1.9. So that's not correct. And these two are obviously greater than 1.9. Our answer is 4D. Question 16. 3 statements about the atom are: the nucleus of the atom is positively charged, the electrons provide only a small fraction of the mass of the atom, and most of the atom is free space. They're all correct. Which statements are correct? All 3. Question 17. The energy levels E of an atom are shown. Which emission spectrum, so our arrows are moving down the way, that's correct, represents the transitions? Okay, well what I've noticed about here is that we have 3 small energy transitions. And given that delta E is equal to hf, that means we have 3 lines close together with small frequencies, okay, or relatively small frequencies. And then this big one here from E5 all the way down to E1, that's a very large energy transfer. So we've got 1, large frequency line. So we'll have 3 close together and then 1 far apart. Let's look at the answers. And interestingly, they've labelled it in increasing wavelength. We can immediately get rid of A and B because they don't have 3 lines close together. And we're looking at C or D. Increasing wavelength means a larger wavelength means a smaller frequency. So we've got a frequency is small up here and frequency is high up there. And what do we say? We needed 3 lines that are close together with a small frequency. So frequency is small here, frequency is high here. 3 lines together with a small frequency are here and one with a higher frequency here. The answer is D.